Good morning, everyone. It's actually good to be indoors when it's snowing outside, isn't it? I'm Bryan Kim, a postdoctoral researcher at Seoul National University, and I'm here to talk about the design trade-offs of SSDs reliability. This work was jointly done between Seoul National University and Dankook University, both in Korea. So before we get into the technical details, I kind of want to give you a high-level overview of the goals of this work. So we want to understand the underlying characteristics of fail-slow symptoms. So fail-slow symptom is when the underlying hardware starts to exhibit errors and starts to fail, and that affecting the overall performance. And this has been demonstrated in large-scale systems. But we wanted to look inside the device and examine the underlying mechanism inside, and more particularly the performance overheads incurred by trying to correct errors and trying to prevent errors. And another goal is that we wanted to think about both system-level and device-level implications for handling errors. And this isn't something that it was explicitly mentioned in the paper, but this is an ongoing work, and hopefully it could generate more discussions afterwards. So going into the details, so how bad is it? How bad are the errors? So this is error rate measurements from an architecture community, and it shows the raw bit error rate in the range of 10 to the negative 7 to 10 to the negative 6. This was measured across, I think, 3 different vendors, including both SLC and MLC chips. And keep in mind that DRAM's raw bit error rate is in the order of 10 to the negative 15. So as it is, it's already pretty error-prone. And it's not getting any better. So one of the main reasons for this is that flash memory vendors are driving for higher density, using smaller process nodes and packing more bits inside a single cell. So the error rate has been increasing, and it's continued till this day. So it's in the range of 10 to the negative 2 to 10 to the negative 3, in that range. And it makes us wonder, how do we build reliable SSDs using faulty or error-prone memories that really don't remember what it was? And the goal of this work is to figure out how do we make SSDs more reliable, and again, what the performance overheads are, and how it changes across different memory chips and different stages of its life. So at its infancy up till its end-of-life stage. So in order to understand this, we first need to look into the error mechanisms of flash memory. And one of the first mechanism is wear-out error. So this is repeated programming erases. The high voltage incurred on the cell eventually breaks down the underlying the structure. And this is a permanent failure that, so vendors usually provide an endurance limit to kind of guide how many times it should be used. Another mechanism is retention error. So this is the charge stored inside the floating gate gradually leaking over time. And unlike the wear out, this is a transient error, so it would go away if it's erased. And lastly, another type of error is disturbance. So this is an unintentional program. A neighboring cell's reading could inadvertently add more charges to the floating gate. So the people at Intel came up with this additive power law based on both device physics, and they correlated with their measurements. And it shows that the raw bit error rate is a function of the number of cycles, how many times it's been programmed and erased, and the time it's been written, time since it's been written, and the number of reads that block has experienced. And the 9 coefficients or parameters in red are something particular to a specific flash memory. So one flash memory would exhibit different types of error characteristics. And in their paper, they correlated with this model with their measurement, but it was based on data from 2009, so it was 10 years ago. So what we wanted to do was see how more recent flash memory behaves. So we went and looked at published data, and we looked at the graphs, and we started extracting the data points. And of course, we're going to lose some, it's not as exact, or it might not be as It's not the exact original data, but it gives you a general idea of the overall characteristics. So with that, we generated an error model for an MLC in 2011, 2015, and more recently, vertically stacked TLC from 2018. So the 9 parameters are different, but it's hard to visualize how they manifest. So this is a graphical visualization of what the error looks like. So this is for the 2011 MLC. And on the y-axis is the raw bit error rate, and the x-axis is how the error manifests. So the first half on the left is how error increases as we increase the wear cycle. And the second half is at 10K cycles, what happens if we leave it for 1 year, or if we read neighboring cells for up to 10K. So for the 2011 cell, the error rate increases as the cells are worn out. And the error caused by retention also increases as we leave it unaccessed for up to a year. And similarly, errors caused by disturbance also increases as we access neighboring cells. So then how would the 2015 chip look like? This is the graphical visualization for the same graph. And 2 things we noticed. First is that there's a dramatic increase in the overall error rate. And the second thing is that it doesn't make complete sense because error rate actually approaches 1, which doesn't really make sense. And what actually happened was that the data set that we had to fit this model had only about up to 1 month of retention time, and this was extrapolated up to 1 year. So this is obviously something that could be potentially improved if we have more data and measurements on raw flash memory. And going on to the vertically stacked TLC, this is what the error looks like. And again, the overall error rate increases. And another big difference is that before, in the previous generations, retention error was sort of the dominating factor. But here, we see that disturbance error has a bigger effect. So with these kind of error models, we could then construct how error handling techniques would work in tandem with these error models. So we're going to look at the 4 different types of error correction and prevention mechanisms, starting with error correction code, data rereads, intra-SSD redundancy, and background scrubbing. Due to the interest of time, I'm going to skip background scrubbing, but just to give you a preview of it, the background scrubbing actually seems to be the least performance detrimental mechanism. And the reason I left it out is because we all want to see what's the bad cases. We don't want to see the best case. So going into how these mechanisms work, I'm sure you're all familiar with all of these, but error correction code basically encodes the payload and adds the parity data to it and programs it together into a flash memory. And when reading it out, both the payload data and the parity data are read out and decoded together. And because this happens for every data transfers, this typically means that it has to be implemented in hardware. So it's not as flexible. It's a design time decision that has to be made. And of course, it incurs hardware cost overhead. So then what happens when ECC fails? So ECC corrects up to a certain number of errors, and what happens in the case if it doesn't work? So recall that both retention loss and disturbance errors either puts more cells in or loses it over time. So this means that the voltage distribution internally could shift over time. So flash memory vendors provide these voltage tuning mechanisms to change where to read. And we could read out, changing the voltage levels, and successfully decode get the right data. And this is, in a sense, similar to how LDPC or soft decision decoding mechanisms work. It repeatedly reads and uses that extra information to get the right data. So in summary, error correction code so hard decision at ECC in particular, tends to have more of a predictable performance, but it's very inflexible because it has to be fixed at the design time. Data reread, which includes that voltage threshold tuning and LTPC, is much more powerful than hard decision ECC, but it increases the latency of reading errors because it has to continuously access the memory. So let's see how data reread mechanisms perform. So this is, the y-axis is normalized response time, and the x-axis is a range of error correction strength. So this is, so given a 1 kilobyte of payload data, how many errors it could correct. And this, we're only showing the result for this 3D TLC, but in the paper there's more results, so I encourage you to check it out. And the performance is normalized to the case when there's no errors at all. So, but this includes garbage collection overhead and blocking due to reads and programs. And this was done on a 4 kilobyte skewed workload. And also we wanted to change the wear state, so how it behaves in the early stage of life to the end of life. So at the early stage of life, we see that if we use a weaker ECC, the performance is bad. And it makes sense because it fails decoding it and then it tries to reread it again, and that incurs performance penalties. And it increases as it wears. So having a higher baseline error rate causes more errors over time. So this shows that, well, the results are somewhat intuitive, but it shows that it's not as, the performance penalties is pretty big. So using a 75-bit ECC engine, it still incurs about a 35% performance overhead at the end of life. But measuring one level deeper, it reveals another interesting aspect to it. So this is the CDF graph of the measured errors. So it shows what's the percentage of data reads with errors below a certain level. So with using an infinite ECC, it says that about 85% of data reads have less than 75-bit errors. But as we use weaker ECC, it drops down further lower. So using a 25-bit ECC, only 50% of data reads have less than 75-bit errors. So this means that continuously reading one piece of data to correct it incurs more errors in the future for other pieces of data. So this makes us wonder, maybe we shouldn't try to correct one piece of data over and over again because it would incur a penalty in the future. So the alternative would be using something like a intra-SSD redundancy where data is reconstructed using other pieces of data. So intra-SSD redundancy is similar to how RAID system works. So flash memory internally, not flash memory, SSD internally has multiple flash memory chips, and data are striped across different flash memory chips. And we could construct a parity data and write it to a different chip. And in the case of one piece of data failing and not being able to read out, we could reconstruct it using a using its data in its stripe group. So intuitively, it shows that intra-SSD redundancy, because we're adding one parity data and writing it, it increases write amplification. And also on errors, because we have to read out multiple pieces of data, it increases read amplification in the case of errors. So let's see how this scheme performs. So again, this is the 3D TLC, and using a baseline of 75-bit error correction engine. And again, we're comparing, normalizing against a scheme where it has no errors. And we're looking at both average response time in the left-hand side and the tail latency in the right-hand side. So at the early stage of life, there's some performance degradation, especially in the tail region, for having a small stripe size. So small stripe size means that we're writing more data for so increases write amplification. And having a large stripe size, s equals 15, means that it mitigates the write amplification, but it would have a larger read amplification on errors. So at the early stage of life, there's not a lot of errors. So there's some degradation, but not as much. But as we degrade, we wear out the chip, we see that the tail latency for having a large stripe size increases dramatically. And this, again, then affects the average performance as well. So in a sense, this might be a controversial statement, but it seems that intra-SSD redundancy has more overheads compared to a simple data reread mechanism. And again, scrubbing seems to be the least detrimental, but you can find more information about it in the paper. So what we observe is that all these mechanisms have downsides to it and performance penalties to it. So simply combining all of these techniques together in hopes to correct errors is not the right way to go. Instead, what we should aim for is to selectively apply these different techniques based on data characteristics. So intuitively, code data, a piece of data that is not as frequently accessed, it's more vulnerable against retention errors. And it would have the least amount of write amplification when using intra-SSD redundancy because it's not something accessed a lot of times. And also, it is likely that code data is identified by garbage collection. So we could piggyback to this existing internal mechanism to identify code data and selectively apply redundancy when writing the garbage collected data. And in a similar sense, read hot data, this is something more vulnerable to disturbance errors. And some prior work shows that we could use the number of read count as the proxy to how badly it is affected to disturbance error, but we could also use the number of data rereads to figure out how badly it is affected. And also, it is likely to be identified by the background scrubber. And lastly, write-hot data. There's not a lot of special attention needed for this piece of data because of the out-of-place update characteristics of flash memory. So we want to see how this fares against other baselines. So we compare against the ECC plus data reread mechanism, so having a baseline ECC of 75-bit correction and repeatedly reading to correct errors. And the second one is an Oracle scrubber. So we assume that it knows all the error rate at any given time. And this is possible because we're looking inside and we're evaluating under a simulated environment. And lastly is the holistic reliability management that selectively applies redundancy and migrates data based on the number of data rereads and the overhead of migrating data. And previously, we looked at synthetic I/O. This time, we're going to look at workload traces. And again, we're normalizing against the case when there's no error at all. For the ECC plus data reread mechanism, and this is done at the end of life stage, we see that it incurs huge overheads for certain types of workloads. For DAPDS, this is the data server for the advertisement, and LMTB, this is a live maps workload. And both of these are very read intensive. And having a read intensive workload and relying solely on reread mechanisms is going to degrade, increase error rates and degrade the performance. For the Oracle scrubber, it reduces the overhead by a large margin. Interestingly, we see that for DAPPS, this is the payload server for the advertisement, it actually increases, the Oracle scrubber performs worse than the data read mechanism. And if we look at the workload statistic, it shows that that workload, it has a very uniform read access pattern. So the 20% top accessed piece of data only accounts for 21% of the traffic. So it's a very uniform workload. So having preventively moving data around is going to increase overhead. And we see that the holistic reliability management, which is something that is more feasible than the Oracle scrubber, performs similarly to the Oracle situation. So the flash memory has been a critical component in data storage for the past 10 years, and it's been driven by increasing density and gaining cost competitiveness. But the downside is that error has been increasing as well. And this is something that we need to think about both at the device level and both at the systems level too, because at this rate, it seems like this going down a very slippery road. So with that, I conclude my talk, and I'll be happy to take questions. Thank you.
Okay, questions, please. In the back first, yes.
Thank you. So you mentioned the intra-SSD, the striping is not as helpful with SSDs. So some of those error characteristics are shared by HDDs as well, right? Like read disturbance. And so why do you think that works for HDDs but is detrimental for, does not work for SSDs?
That's a very good question. One possibility is that error rate in flash memory, it has a more of a, it's a function of its past history, meaning that its number of P cycles and the number of reads and the time it's been written is strongly correlated. And hard disk drive errors are, tends to be more random and sporadic, although bursty if it happens. So these characteristics make it likely that if one piece of data has errors, the other stripe group data also has errors, and this is something that needs to be addressed for SSDs.
So you think this is more specific for, this problem is more specific for SSDs than for HDDs?
Yes, I do. But at the same time, this work doesn't address random errors. So we're assuming that all the error rate follows this nice curve. But again, this is only a probability. So there's going to be these rare cases where it suddenly dies, or even a chip might fail. And there's no other way to address that aside from redundancy. So.
Hi, thank you for your talk. Renshou Liu from National Tsinghua University. I have two questions. The first one is by disturbs, do you mean read disturbs or write disturbs or both? And the second question is in about page 35, you mentioned that rereading NAND flash cause penalty in the future. Can you elaborate more on this? Do you mean read disturbs effect? Thank you very much.
Certainly. So by disturbance, I'm focusing on read disturbance. And as you mentioned, there exist program disturbance effects too. But this is somewhat mitigated by the sequential programming constraints followed by manufacturers. And what I meant by this is that if we're reading it again, so data rereads aren't, you entirely have to access the flash memory array again. And this act itself increases the chance of read disturbance affecting neighboring cells. So this increases the overall error rate for the future.
Okay, we don't have any more questions. Let's thank the speaker once more.
Thank you.